So here we have this cannon set at 30 degrees and this is a basket also set at 30 degrees. Now if the projectile is launched at 30 degrees, it lands in the basket. Now what will going to happen if the launching angle is changed to 60 degrees and the basket is also set at 60 degrees? Will the projectile still lands in the basket? This is the question. Think. Now before discussing the answer, we will discuss some concept related to it and then we'll get back to this question. Let's discuss one more symmetry of projectile motion. So we have a projectile launched with an initial speed of 20 meters per second. And I have drawn two graphs for this projectile. First graph is the range versus the launch angle of projectile. Second is the height versus the distance of projectile. Now one important note here is that we have not considered the effect of air resistance while sketching these graphs. So let me first explain these graphs. This is the range here and this is the launch angle, and this is the launch angle 30 degree, this is the launch angle 60 degrees, and this is the launch angle 15 degrees, and this is the launch angle 75 degrees. So if you see if the launch angle is 30 degree and 60 degree, the range is same in between 30 to 40. And if the launching angle is changed to 15 degrees and 75 degrees, then also the range is same, that is 20 meters. And here in the second graph we have this is the launch angle at theta equals to 30 degree and this is theta equals to 60 degrees. Now you may see that the launching angle is changed, but the distance traveled horizontally by the projectile before landing is same in both the case, but the difference is that the height, the maximum height achieved by the projectile is different. In case of 60 degree, the vertical distance traveled by the projectile is more, and it's very obvious that this green is for theta equals to 45 degrees because here the range is maximum. Okay, so what we can conclude from here, that launch angles equally greater than or less than 45 degrees, such as 30 degrees, 60 degrees and 15 degrees, 75 degrees, will have the same range, which you can see in this figure. Or in other words, we can say for a given projectile, if you are dealing with two different angles whose sum equals 90 degrees, then the range in both case will be same, as you can see from this also, from this figure also. But what will be the difference? The maximum height attained by the projectile will be different, that you can understand from this graph. Like when the projectile was launched at 30 degree, the maximum height achieved is this, but when the launching angle changes to 60 degrees, the maximum height this time is this, but the range is same in both the case. Now you will be able to give the answer for the question that I asked in the starting of the video. So if the angle is changed to 60 degrees, the projectile still lands in the basket, because if you see the sum of 30 degrees and 60 degrees, it is 90. So that is why in this case, for this particular case, the projectile will definitely land in the basket. Now I'll be writing the important point that we can conclude from this. The first point is the launch angle that are greater or less than 45 degrees by the same amount gives the same range. For example, projectile with theta equals to 30 degrees and 60 degrees will follow the different path but will have the same range. And all these things that we have studied are valid only if there is no air resistance and the projectile is launched with same speed. This is a very important point. Now let's take an example. So here we have a fish that hunts an insect resting on the leaf. Now suppose that the fish squirts water with an initial speed of 2.30 meter per second and at an angle 19.5 degrees above horizontal. And it is also given when the stream of water reaches a beetle on the leaf, it is moving horizontally. That you can see in this image. The water is moving horizontally when it reaches near the insect. Okay. Now there are three parts in this question that we need to solve. In the A part, we need to find how much time does the beetle have to react. So basically what we have to find the time taken by the water to reach to the leaf. This is what we have to calculate in the A part. Now because the stream of water is moving horizontally when it reaches the insect, it means the water is at top of its parabolic trajectory. So we can say that the vertical component of velocity at this point is 0. That is, we can write that Vy is 0 here. And we can use this equation Vy is equals to V0y plus At. And in this case, this should be Ay. And Ay we have minus G. And Vy is 0 at this point. So we can write this is 0 is equals to V0y is, in the vertical direction, this component of velocity will be V0 sine theta. So this will be V0 sine theta minus Ay is, this is G times T. Now from here the expression for time will get this equals to V0 sine theta divided by G. Now we have all the values, we can plug it here to find the time taken by the water to reach at the top of its trajectory. So this time t will be equals to V0 we have 2.30 meter per second, and sine theta, theta is 19.5 degrees, divided by G is 9.81 meter per second squared, and on further solving we'll get the time to be equals to 0.0783 second. So this is the time the insect have to react. So this is the answer for the A part. Now next in the B part we have to find the height h. This height h we have to find. So for that we can use this equation. This is the B part that we are solving, and I can use this equation. Y is equals to y0 plus v0y times t plus ay 1 over 2 ay t square. Now here ay is minus g and y0 is 0 because this is the initial position y0, and here we have taken it to be origin, so y0 is 0, and v0y we already know it is v0 sine theta. Now this is y in this case will become h. So this would be h is equals to, this is 0 plus this is v0 sine theta times t. Now at this point we calculated time to be this, so we can put it here. This is v0 sine theta over g, this is t, plus 1 over 2 ay is minus g, so I can write this is minus g t square. T we have v0 sine theta over g and its whole square. Now we can solve it further and we'll get the expression for h to be equals to v0 sine theta whole square divided by 2g. Now basically this height is the maximum height achieved by the projectile when it reaches to the top of its trajectory. This is basically h max we can write. So now we can put the values to find the h. V0 we have 2.30, sine theta is 19.5 and its whole square divided by 2 times 9.81 meter per second squared, and on further solving we'll get this height to be 0.030 meter. So this is the answer for the B part. Now next in the C part we have to find the horizontal distance d. This part is pretty simple. We know that the horizontal velocity remains the same, so this d will be equals to the speed multiplied with time. Speed we have v naught cosine theta in the horizontal direction, and time t as it is. Now we can put the values. This is 2.30, cosine theta is 19.5, and time we already calculated to be 0.0783, and on further solving we'll get this distance to be 0.170 meter. So this distance d is 0.170 meter, and this h height is 0.0300 meter. So this is the answer for the B and the C part. Now I'll be giving one question to you, and the question is this. It says that a baseball player throws a ball to another player, and the initial speed of the ball is v naught, and it is thrown at an angle 45 degrees above horizontal. That means he throws the ball like this with the initial speed v naught, and this is 45 degrees above horizontal. Now what we have to tell, is there ever a time during its flight to the other player when its speed is 1/2 v naught? So during the time of flight, is there any moment when the speed becomes half of v naught? This is what you have to tell. And I'm just writing the answer. You have to explain on your own. The answer would be no. This is not possible. And you have to explain it in your own words that why it is not possible in the comment box below. If you find any confusion, you can always comment B. I'll definitely write the answer for you. With this, chapter 4, that is kinematics in 2-dimensional, is over. Now we'll review all the topics that we studied in chapter 4. First topic that we discussed was motion in 2 dimension, and under this topic we studied the independence of motion. That is, motion in x and y direction are independent of one another. Next we discussed the projectile motion and the basic equations. So projectile is an object that is thrown or launched into motion and then allowed to follow a path determined only by the influence of gravity. And projectile motion refers to the path of an object after it is thrown, kicked, or otherwise launched into the air. So here we have this projectile launched into the air, and this is a trajectory. This direction shows the velocity, and this is the direction for acceleration A, which in this case is -g. And then we derived some basic equations for this projectile motion, and these were the basic equations that we derived. Then next we discussed the zero launch angle when the projectile is launched horizontally, like here the theta is equals to 0. Then what we call this as the zero launch angle. And we also derived the equations of motion when a projectile is launched horizontally. So in this case we can take that x naught we have 0, and the initial position y naught is h, and we derived some basic equation for this motion. The first one was x equals to v naught times t, then y is equals to h minus 1/2 gt square, and then we discussed that vx is equals to v naught, that is the horizontal velocity remains the same, and vy we have minus gt, then vx square is equals to v naught square, and finally vy square is equals to minus 2g delta y. These were the equations that we derived. And we also saw that this curve is a parabolic path, and we also derived the equation for this path, and the equation was y is equals to h minus g over 2 v naught square times x square. This is the equation for this curve. Then next we discussed the general launch angle when the projectile is launched at an arbitrary angle theta with some speed v naught. And we derived some basic equation for this motion, and the equation that we derived were x is equals to v naught times cosine theta times t, and y we have v naught sine theta times t minus 1/2 gt square. Then we discussed vx is equals to v naught cosine theta, the x component of velocity, and vy is v naught sine theta minus gt. The x component of velocity remains the same throughout the motion, but this varies. And then finally we have a Vx square is equals to V naught square cosine square theta, and Vy square is equals to V naught square sine square theta minus 2g delta y. These were the equations that we derived under this topic. And then we discussed the key characteristics of the projectile motion. The first characteristic was its range. Range is the horizontal distance traveled by the projectile before landing. This is what we call the range. And we also derived the expression for range, r, to be equals to v naught square over g times sine 2 theta. And then we also derived the expression for the time of flight t, which was 2 v naught over g times sine theta. It is the time taken by the projectile from the starting point to the landing point. And then we also discussed the maximum height achieved by the projectile. This is the maximum height, h max. We took one example on this, and we derived the expression for h to be equals to v naught sine theta whole square over 2g. And we also discussed the symmetry of projectile motion, that at a given height the speed of the projectile is same on the way up as on the way down. For example, that if you take the same height like this at this point and at this point, same height, it is moving with some speed, say v naught, then at the same height the speed would be same, this v naught would be same, but the velocity will be changed because the direction is changed, but speed at both the point will be same. This is symmetry of the projectile motion. So at any height the speed is same on the way up as on the way down. So this is all we studied in chapter 4, and now next we'll discuss the questions that is given in the book James S. Walker.